Hey everyone, and welcome back. Tonight, we are doing something truly restful, explaining how AI actually works. Not the marketing version, where a glowing blue face stares out of a screen and promises to revolutionize your toothbrush. Not the panic version, where a machine becomes self-aware because someone gave it access to a spreadsheet. Just the ordinary, slightly less glamorous reality of how modern AI systems work, why they can seem surprisingly clever, and why, underneath all the headlines, they are still built from mathematics, data, electricity, and an almost unreasonable amount of expensive hardware. The first thing to understand is that AI is not one single machine, one single method, or one single magical idea. It is a very broad label that covers a large collection of techniques for getting computers to do tasks that seem intelligent. That is all. If a machine can recognize a face, recommend a song, predict the next word in a sentence, identify a tumor on a scan, or tell you with alarming confidence that your blurry photo contains either a chihuahua or a muffin, people tend to call it AI. The term is useful, but also slightly messy, because it bundles together many different systems that operate in different ways. So when people ask, how does AI actually work, there is a slightly annoying but very necessary answer, which is, it depends on which kind of AI you mean. A chess engine works differently from a voice assistant. A recommendation algorithm works differently from a self-driving perception model. A spam filter works differently from a large language model. They all live under the same umbrella, but the umbrella is very large, and some of the people underneath it are doing completely different jobs. That said, many modern AI systems do share a common basic idea. They learn patterns from data. That is the heart of it. You give the system a large amount of examples, it adjusts internal numerical settings to fit those examples. And then it uses what it has learned to make predictions on new inputs it has never seen before. In other words, modern AI is often less like carefully programming a machine with a long list of explicit rules, and more like exposing it to vast numbers of examples until it becomes very good at noticing patterns humans would struggle to manually encode. This is the key mental shift. Traditional programming usually works like this. A human writes exact instructions. If condition A happens, do B. If the number is above 10, subtract 3. If the user clicks the button, open the menu. The logic is explicit. Someone wrote the rules, and the computer follows them. But many real-world tasks are very hard to express as neat rule lists. Think about recognizing a cat in an image. You could try to write rules. Cats have pointy ears, they have whiskers, they have fur. They tend to have certain body proportions. That sounds reasonable until the cat is sleeping upside down in a cardboard box, one ear hidden, poor lighting, blurry image, and a suspiciously cat-shaped blanket nearby. Very quickly, the rule list becomes miserable. Humans are good at this kind of pattern recognition because our brains are adapted for it. Computers are not. Unless we build systems that can learn from lots of examples. So instead of writing all the rules for catness, modern machine learning says, let's give the system millions of labeled examples of cats and non-cats. Let it adjust itself and allow it to discover useful patterns on its own. That phrase, machine learning, is important because it describes the dominant approach behind much of what people currently mean when they say AI. Machine learning is a subset of AI. It refers to methods where systems improve performance by learning from data, rather than relying only on fixed, handwritten rules. And within machine learning, the most famous family today is deep learning, which uses neural networks with many layers to learn extremely complex patterns. Now, neural network is one of those terms that sounds both scientific and faintly theatrical. It is inspired by the brain, but not in the way people sometimes imagine. A neural network is not a tiny artificial brain with thoughts floating around in it like a science fiction aquarium. It is really a big function made of many smaller mathematical operations stacked together. Its job is to transform input data into output predictions. Suppose the input is an image. The output might be dog, or car, or stop sign. Suppose the input is a sentence. The output might be a translation, a summary, or the next most likely word. Suppose the input is audio. The output might be a transcription. The basic mechanism is the same. Numbers go in, many layers of computations happen. Numbers come out, and those outputs are interpreted as predictions. To understand this more concretely, we need to zoom in on a simpler example. Imagine a system that predicts house prices. You feed in a few features: square footage, number of bedrooms, neighborhood, age of the building. The system combines these inputs with adjustable numerical values called weights. If square footage matters a lot, that weight may become large. If the age of the building matters less, that weight may be smaller. The system calculates an output, compares it to the true house price in the training data, measures the error, and then adjusts the weights to reduce that error. Repeat this on many examples, and the model gradually learns how to map input patterns to output predictions. That simple setup is already the essence of machine learning. A model is a parameterized function. Parameters are numbers the system can adjust. Training means changing those numbers so that the model becomes better at matching the data. If you remember only one technical sentence tonight, that is not a bad one to keep. Now let's make this slightly less dry, though only slightly, because that would be reckless. Imagine you are trying to teach a very patient clerk to guess whether an email is spam. At first, the clerk is terrible. Every message is a mystery. But after seeing enough examples, the clerk starts noticing patterns. Messages with certain phrases, certain links, certain suspicious claims about urgent inheritances from distant princes all begin to look similar. The clerk is not necessarily reasoning like a person. The clerk is discovering statistical regularities. That is how many AI systems work. They are pattern detectors refined by repeated exposure to data and corrected using feedback. The correction process is crucial. A model does not simply stare at data and awaken. It needs a training objective, a way to measure how wrong it is. This is usually done using a loss function. The loss function is a number that tells the model how bad its current prediction was. If the model predicts the wrong label, the loss is higher. If it predicts something close to the correct answer, the loss is lower. Training is the process of adjusting parameters to minimize this loss across many examples. And how does it adjust those parameters? Usually through a method called gradient descent, or one of its many improved descendants. This is one of those phrases that sounds far more elegant than it feels when implemented at scale. The basic idea is that the model computes not only how wrong it was, but also how each internal parameter contributed to that wrongness. Then it nudges those parameters in the direction that should reduce the error. It takes a tiny step, then another, often millions or billions of times. A helpful analogy is hiking downhill in dense fog. You are standing somewhere on a giant landscape, and your altitude represents how wrong the model is. Your goal is to get lower. You cannot see the whole mountain, but you can feel the local slope beneath your feet. So you take a small step downward, then another. That is roughly what gradient descent does in a very high-dimensional mathematical space with more coordinates than anyone should have to think about before bed. Now, let's connect this to neural networks. In a neural network, each artificial neuron takes some inputs, multiplies them by weights, adds them together, and then applies a function to decide what signal to pass on. One layer feeds into another. Early layers may capture simple patterns. Later layers combine those into more complex patterns. In image systems, early layers might detect edges, corners, or textures. Deeper layers might detect shapes, parts of objects, and eventually whole categories like faces or bicycles, or the universally haunting category of things that might be a toaster. In language models, the story is different in detail, but similar in spirit. Instead of pixels, the input is text. But computers do not understand text as letters or words in the human sense. They convert text into numbers. Usually language is broken into pieces called tokens. A token might be a whole word, part of a word, punctuation, or some other unit, depending on the model's tokenizer. The model processes sequences of these tokens and learns statistical relationships between them. This brings us to one of the central facts about large language models. At a fundamental level, they are trained to predict the next token. That sounds underwhelming, and many people hear it and say, surely it must be more than that. But no, that really is the astonishingly plain core. During training, the model sees billions of pieces of text and repeatedly tries to guess what comes next. It guesses, it is corrected, it adjusts its parameters, and over time, it becomes extremely good at predicting plausible continuations. Now, this is where something interesting happens. Predicting the next token well in human language turns out to require learning quite a lot about the world, or at least about how the world is described in text. To predict the next word in a medical article, the model needs some grasp of medical terminology and structure. To continue a legal paragraph, it must capture legal phrasing and logic. To answer a question about history, it needs patterns connecting people, places, and events. It does not understand these things exactly as humans do, but it builds rich internal representations that encode many useful relationships. That is one reason these models can feel more intelligent than their training objective sounds. Predicting the next token is simple to state, but solving it at a high level across vast amounts of human language is not simple at all. Language carries facts, conventions, social cues, reasoning patterns, narrative structures, jokes, formulas, instructions, arguments, and every other delightful burden of civilization. A model that becomes good at predicting language absorbs statistical traces of all of this. Still, it is important not to exaggerate. A language model does not have beliefs in the ordinary human sense. It does not sit in quiet contemplation between prompts. It does not privately worry about whether it left the metaphorical stove on. What it has is a huge set of learned parameters that shape how it transforms input text into likely output text. It can simulate many forms of reasoning, explanation, style, and conversation because those patterns exist in the data and because the architecture is powerful enough to model them. But that is not the same as conscious understanding. Now, let's slow down and talk about data, because data is the fuel and the shaping force behind AI. Without data, most machine learning systems are useless. The model cannot learn patterns from nothing. If you want an AI to recognize tumors, you need medical scans. If you want it to understand speech, you need audio and transcripts. If you want it to generate fluent language, you need enormous quantities of text. The quality of that data matters tremendously. If the data is biased, incomplete, mislabeled, low quality, or unrepresentative of the real world, the model will inherit those flaws. Machine learning is often described as if the model were some independent genius, but much of its behavior is determined by the examples it sees. Show it skewed examples, and it learns skewed patterns. Show it noisy labels, and it learns confusion. Show it narrow data, and it fails outside that narrow range. This is why people sometimes say, garbage in, garbage out. It is not a glamorous slogan, but it has the decency to be true. AI systems can be dazzling, but they remain deeply dependent on the data used to train them. If a facial recognition model is trained mostly on certain demographic groups, it may perform worse on others. If a hiring model learns from biased historical decisions, it may reproduce those biases. If a chatbot is trained on flawed internet text, it may learn flawed internet habits, which is one of the least surprising developments in modern history. Another issue is that data is not just raw material. It is also compressed experience. A model does not observe the world directly in the rich, embodied way humans do. It sees curated slices, pictures, words, audio clips, sensor streams, labels. Its knowledge is mediated through representations. So what the model can learn depends heavily on what kinds of signals are available and how they are organized. This leads us to supervised learning, unsupervised learning, and reinforcement learning, three broad training paradigms that are often mentioned together, usually with an air of organized sophistication. In supervised learning, the model learns from examples that include both inputs and correct answers. Image plus label, audio plus transcript, email plus spam or not spam tag. The model predicts the answer, compares it to the known answer, and adjusts accordingly. This is straightforward and very powerful, but it requires labeled data, which can be expensive and slow to produce. In unsupervised learning, or more broadly self-supervised learning, the model tries to discover structure from data without relying on explicit human labels for every example. Language model training is often described as self-supervised because the text itself provides the signal. If you remove or hide part of the text, the next token becomes the target. No human has to sit there labeling every sentence as the next word should be banana. The data naturally contains the training objective. Then there is reinforcement learning, where an agent takes actions in an environment and learns from rewards or penalties. Imagine teaching a system to play a game. It tries moves, sees outcomes, and learns which choices lead to higher reward. This approach is powerful in settings where trial and error is possible, and goals can be defined in terms of reward, such as games, robotics, or some control tasks. For chatbots and advanced language assistants, reinforcement learning is often used after the main pre-training phase to make the model more helpful safer, or better aligned with human preferences. In simple terms, after the model has learned language broadly, people can rank outputs or provide feedback, and the model is further tuned to produce responses that better match what humans want. This is one of the reasons a modern assistant can sound more conversational, cooperative, and polished than a raw next token machine trained only on text prediction. But before we get too far into alignment and fine-tuning, it is worth pausing on the scale of modern AI, because scale changes the story dramatically. Many earlier machine learning systems were relatively specialized. They used smaller data sets, smaller models, and narrower tasks. But recent advances, especially in large language models and generative systems, came in large part from simply doing everything on a grander scale. More data, larger models, more computation, more training time. When people say a model has billions or hundreds of billions of parameters, those parameters are the adjustable numbers learned during training. They are not facts stored one by one like books on a shelf. Rather, they are distributed pieces of a giant pattern space. Information is encoded across them in complex ways. One parameter alone means very little. It is the collective arrangement that matters. Training such a model is not like running a laptop overnight while hoping for the best. It requires vast amounts of computational power, often using specialized hardware like GPUs or TPUs. These chips are particularly good at the kinds of matrix operations neural networks rely on. During training, huge numbers of calculations are performed repeatedly across giant data sets. It is expensive, energy-intensive, and logistically complicated. This is one reason only certain organizations can train the very largest frontier models from scratch. Now, you may wonder, if AI is mainly learning patterns, does that mean it is just memorizing? The answer is partly, but not only. A model can memorize some training data, especially if the data is repeated or unusual. But if it only memorized, it would be almost useless on new examples. What makes machine learning valuable is generalization, the ability to perform well on inputs it has not seen before. The model learns underlying regularities that let it extend beyond exact copies. Think of a child learning the concept of a chair. The child does not memorize one chair and then collapse emotionally in the presence of all future furniture. The child notices patterns, flat surface, legs, or support designed for sitting. Then the child can recognize many different chairs. Machine learning aims for something like this, though in more mathematical form and with fewer crayons. Generalization is difficult. If a model is too simple, it may underfit, meaning it fails to capture important patterns in the data. If it is too flexible, it may overfit, meaning it learns the training data too specifically and performs poorly on new cases. Good training involves balancing these forces so the model captures the real structure rather than the accidental noise. This is one reason evaluation matters. You do not judge a model only on the data it trained on. You test it on separate data it has not seen. This helps estimate whether it has learned something general or merely gotten comfortable with the exact examples in front of it. In practice, people split data into training, validation, and test sets. The training set is used to learn. The validation set helps tune choices during development. The test set gives a final estimate of performance. Of course, real life enjoys making this harder than it sounds. Benchmarks can be gamed, data sets can leak, and a model can perform beautifully in the lab but stumble badly in the messy unpredictability of reality. Humans are very good at building clean demonstrations and then acting surprised when the world turns out to contain glare, accents, ambiguity, sarcasm, and weather. All of this brings us back to the quiet core of the matter. AI works not because machines have suddenly acquired souls, nor because a hidden engineer is manually typing the answers from behind a curtain, but because statistical learning at scale can produce systems that map complex inputs to useful outputs with remarkable effectiveness. They do this by optimizing many parameters over large data sets, discovering patterns that enable prediction, classification, generation, or decision support. And yet, that sentence, while technically respectable, does not fully explain the strange feeling people get when a model writes an essay, draws an image, or answers a question in a tone that sounds almost thoughtful. To understand that feeling, we need to go deeper into representation, architecture, attention, training stages, fine-tuning, and why generative systems can produce outputs that seem original while still being grounded in learned statistical structure. That is where we are heading next. In the next part, we will look more closely at how modern language models process text, what embeddings are, why transformers became so important, how attention works without being magical despite the name, and how a model turns a sequence of tokens into something that sounds uncannily like a person who has had too much coffee and access to the entire internet. Gently, though. No need to rush into the machine. Let's begin with text, because text is where many people first met modern AI in a form that felt strangely conversational. When you type a prompt into a language model, the system does not see elegant thoughts or glowing intentions. It sees tokens. These are chunks of text produced by a tokenizer, which is a system that breaks language into manageable pieces. Sometimes those pieces are whole words. Sometimes they are parts of words. Sometimes they are punctuation marks, spaces, or fragments that look like they were chosen by a committee that had grown tired and slightly cynical. But they are useful because they turn messy human language into a sequence of discrete units a model can process. A sentence like, "How AI actually works," might be split into a few tokens. Those tokens are then converted into numerical representations. This is where embeddings enter the story. An embedding is a learned vector, which is a list of numbers that represents a token in a high-dimensional space. In plain language, it is the model's way of turning symbolic text into something mathematical it can manipulate. Now, that phrase, high-dimensional space, can sound like the sort of thing a tired professor says right before everyone quietly regrets attending. But the idea is not too bad. Imagine that every word or token gets placed somewhere in a giant abstract map. On this map, tokens with similar usage patterns tend to end up closer together. Words related to food may cluster in one region, words related to law in another. Certain verbs, pronouns, numbers, punctuation marks, styles, and grammatical patterns all develop relationships based on how they appear in the training data. The model is not reading meaning in the way a person does, but it is learning a geometry of usage. This is one of the first places where AI starts to feel less like a pile of rules and more like something uncannily fluid. It is not merely matching exact phrases. It is building internal structures that capture similarities and relationships. If doctor and physician appear in related contexts, their embeddings may reflect that. If Paris often occurs near language about France, travel, art, or geography. Those associations can influence how it is represented. A great deal of apparent intelligence comes from these learned structures. But embeddings alone are not enough. A model also needs to know where each token appears in a sequence, because order matters. Dog bites man and man bites dog contain the same words, but the newspaper interest level is quite different. So the model includes positional information, which helps it distinguish not just what the tokens are, but where they sit relative to one another. Once the tokens are embedded and given positional information, they pass through layers of the neural network. In older approaches to language modeling, sequence processing often relied on recurrent neural networks or similar architectures that processed text step by step. These could work, but they had limitations, especially when trying to capture long-range dependencies. If a sentence began with something important and did not resolve until many words later, the model could struggle to maintain that context. This was inconvenient because human language enjoys inserting clauses, parenthetical asides, and decorative nonsense over long stretches before finally landing the point. Then came the transformer architecture, which changed the field dramatically. Introduced in 2017, transformers became the foundation of many powerful modern language models. Their key innovation was a mechanism called attention. Attention is one of those names that sounds poetic, but the underlying idea is practical. Instead of processing a sequence strictly one token at a time and carrying information along in a narrow chain, the model can, in effect, look at many parts of the sequence and decide which other tokens are most relevant when processing the current one. That is a major advantage. Suppose you are reading the sentence, "The old book on the shelf near the window, which had been damaged by rain years earlier, was finally restored." To understand what "was finally restored" refers to, you need to connect it back to book, not window or rain. Attention helps the model do this by learning which earlier tokens matter most for interpreting the current one. In more technical terms, each token representation is used to produce three vectors called queries, keys, and values. These are compared with one another to determine how much each token should attend to other tokens. The model computes attention scores, uses them to weight information from across the sequence, and combines that information into updated representations. The result is that each token can be interpreted in the context of the others. This sounds elaborate because it is elaborate, but the outcome is intuitive. Words are understood not in isolation, but in relation to surrounding words. The meaning of bank in Riverbank differs from bank account. The role of light in light meal differs from light bulb. Attention helps the model resolve such context-dependent meaning by looking at relevant parts of the sentence. Transformers also use multiple attention heads, which means the model can look for different types of relationships at the same time. One head might focus on syntax. Another might track longer-range references. Another might pick up punctuation patterns. Another might help with stylistic flow. We should be cautious not to imagine each head as a tiny scholar wearing spectacles and specializing in subordinate clauses, but different heads do learn to capture different aspects of structure. After the attention operations, the representations pass through feed-forward layers, normalization steps, residual connections, and other architectural components that help learning remain stable and expressive. Layer after layer, the model refines its internal representation of the input. By the time the final layers produce output probabilities for the next token, the model has transformed the original sequence through a deep stack of learned computations. And then comes the moment people notice most: generation. The model produces a distribution over possible next tokens. It does not begin by choosing a whole paragraph. It chooses one token at a time. Each newly generated token is appended to the context, and the process repeats. This means every sentence you read from a language model is, at its core, assembled incrementally. One piece leads to the next, then the next, then the next, until you get something that sounds like a finished thought. There is something almost comfortingly mundane about this. The machine is not unveiling a fully formed speech from a hidden chamber. It is making a series of constrained probabilistic decisions, each informed by the context so far. Yet, when the model is large, well-trained, and tuned carefully, those local choices can produce surprisingly coherent global behavior. A paragraph seems planned. An explanation seems structured. A story seems paced. Much of that coherence emerges from the model's learned ability to maintain patterns across long sequences. Of course, next token prediction alone does not determine everything. The way a model samples from the probability distribution matters too. If it always picks the single highest probability token, the output may become repetitive, stiff, or overly predictable. If it samples too freely, the output may become chaotic, as if the machine had decided that grammar is a colonial construct and accuracy optional. So generation uses strategies like temperature, top K sampling, or nucleus sampling to balance coherence and variety. Temperature is a parameter that adjusts how sharp or flat the probability distribution is. Lower temperature makes the model more conservative. Higher temperature makes it more adventurous. With a low temperature, the model will tend to choose safer, more likely continuations. With a higher temperature, it may produce more creative or unexpected phrasing, though sometimes at the cost of reliability. One might say the model becomes more willing to improvise, which is charming in poetry and less charming in medical dosing instructions. Now, all of this describes the forward process of using a trained model. But we should return to training itself, because that is where the real labor lies. A large language model is not born with language. It is trained over enormous data sets containing books, articles, websites, code, forums, documents, and other text sources, depending on the data pipeline. During pre-training, the model repeatedly sees sequences of tokens and learns to predict missing or next tokens. The goal is not to teach it one narrow task, but to build a broad statistical model of language. Over time, this pre-training phase gives the model a kind of general linguistic competence. It learns grammar, style, common facts, discourse patterns, many forms of explanation, and the ability to continue text across countless domains. But a raw, pre-trained model is not always ideal for interactive use. It may ramble, produce unhelpful answers, ignore instructions, or continue a prompt in an odd direction simply because that is statistically plausible. Pre-training teaches language. It does not necessarily teach manners. This is where fine-tuning comes in. Fine-tuning means taking the pre-trained model and training it further on more specific data or objectives. For example, if you want a model to follow instructions, you can fine-tune it on prompt response pairs. If you want a medical summarization system, you can fine-tune it on curated examples in that domain. If you want a customer support assistant, you can fine-tune it on support conversations and desired response styles. The pre-trained model supplies general knowledge of language. Fine-tuning shapes it toward a particular role. Instruction tuning became especially important for making language models useful as assistants. Instead of merely continuing text, the model learns that when a user asks a question, it should answer the question. When a user requests a summary, it should summarize. When a user asks for a list, it should usually produce one rather than wandering into reflective poetry about bullet points and their emotional burden. This seems obvious to humans, but it is not built automatically into pure next token prediction. It has to be taught. After instruction tuning, many systems also use human feedback to improve response quality. Human evaluators may compare multiple model outputs and indicate which one is better, according to criteria like helpfulness, accuracy, clarity, harmlessness, or style. A reward model can then be trained on these preferences, and reinforcement learning can further adjust the language model to produce outputs more aligned with those preferences. This is often called reinforcement learning from human feedback, though there are related methods and variations. This process does not grant the model a moral compass in the human sense. What it does is shape behavior statistically. The model becomes more likely to produce responses that humans have judged preferable in similar contexts. It is less like giving a machine values through philosophical awakening, and more like repeatedly training an overpowered autocomplete to behave better in polite society. Still, even with fine-tuning and feedback, models remain imperfect. One important reason is that they generate plausible text, not guaranteed truth. This leads us to one of the most discussed problems in language models: hallucination. In this context, hallucination means the model produces content that sounds confident and coherent, but is false, fabricated, or unsupported. It may invent citations, misstate facts, create non-existent laws, or cheerfully attribute quotes to people who never said them. Why does this happen? Because the model's training objective is to generate likely continuations, not to verify truth against an external ground reality. If the prompt and context suggests that a detailed answer should follow, the model will produce one based on patterns it has learned. Most of the time, this is useful. Sometimes, unfortunately, it is also wrong. The model is not deliberately lying. It is doing what it was trained to do: generate text that fits the context. Truthfulness is something we try to encourage through data, tuning, retrieval, tool use, and evaluation, but it is not automatically guaranteed by fluent language generation. This distinction matters enormously. Fluency is not the same as understanding. Confidence is not the same as certainty. Style is not the same as substance. Human beings are also known to confuse these things from time to time, but AI can do it at industrial scale and in perfect punctuation. One way to improve factual reliability is retrieval augmentation. Instead of relying only on what the model learned during pre-training, the system can search an external knowledge base, database, or document collection at inference time, retrieve relevant information, and feed that information into the model as context. Then the model answers using both its general linguistic ability and the retrieved evidence. This helps ground the response in current or verifiable information. You can think of this as giving the model notes before it speaks. The model still generates the response, but it does so with supporting material in view. This can reduce hallucinations, improve freshness, and allow the system to answer questions about documents or domains that were not fully captured during training. It is also one reason many practical AI systems are not just a standalone language model, but a combination of model plus retrieval, memory, tools, orchestration logic, filters, and interfaces. Tool use is another major step forward. A model by itself can predict text, but if the system lets it call external tools, it can do more grounded work. It can use a calculator for arithmetic, query a database, run code, search the web, check a calendar, or interact with software systems. In such setups, the model acts less like a sealed oracle and more like a coordinator. It interprets the user's request, decides when a tool is needed, invokes it, reads the result, and then explains or acts on that result. This is significant because many tasks humans care about require more than raw language generation. They require access to the world. A model cannot reliably answer a question about today's weather from pre-training alone. It needs current data. It cannot always solve a complex calculation reliably through text generation alone. A calculator helps. It cannot know your schedule without being connected to it. Tools extend the system beyond its internal parameters. We should linger here because this is part of how AI is actually becoming useful in everyday systems. Not by replacing every software component with one giant mystical brain, but by integrating probabilistic language reasoning with structured tools and data sources. The model handles interpretation, planning, and explanation. Other systems handle precise retrieval, storage, computation, and action execution. It is less a single mind than a collaborative workflow built around a powerful language interface. Now let us shift to other kinds of AI beyond text, because the general principles remain similar even when the data changes. In computer vision, the input is usually an image or video. The system must convert visual information into useful outputs: labels, bounding boxes, segmentations, depth estimates, actions, identities, or generated images. The model again learns patterns from data. Instead of token sequences, it works with pixel arrays or visual patches. Instead of grammatical relationships, it learns spatial and semantic relationships. Convolutional neural networks were historically dominant in vision tasks. They use filters that slide across an image to detect local features, such as edges, corners, and textures. As layers deepen, the model can combine these local signals into more abstract features: eyes, wheels, fur, doors, road markings, and so on. Convolutions were effective because they exploit the spatial structure of images and share parameters across locations, making learning efficient. More recently, transformer-based methods have also become important in vision, where images can be divided into patches and processed similarly to token sequences. The specific architectures vary, but the broad pattern is familiar. Represent the input numerically, apply many learned layers, optimize on large datasets, and map the result to useful outputs. For speech AI, the input is audio. The system may first transform waveforms into features such as spectrograms, which represent frequency information over time. Then models learn to map these patterns into phonemes, words, speaker identities, emotional cues, or synthesized speech. Again, the model is learning regularities from examples. It does not hear as humans hear, but it learns correlations between acoustic patterns and linguistic or speaker-related outcomes. Generative AI extends these ideas further. Instead of only classifying inputs, generative models produce new outputs: text, images, music, code, video, speech. This feels magical because the machine is not simply choosing from a fixed list. It is creating novel combinations. But novelty here emerges from learned probabilistic structure. The model has internalized patterns from training data and uses them to generate outputs that are new in combination, even if grounded in familiar distributions. Take image generation. A model trained on many images and text descriptions learns relationships between words and visual patterns. When asked for a sleepy scientist in a dim laboratory, it generates an image by sampling from that learned distribution. Depending on the model type, it may do this through autoregressive generation, diffusion, or another approach. Diffusion models, for example, learn to gradually denoise random noise into a coherent image guided by text. The process is mathematically sophisticated, but the essential idea is that the model has learned what kinds of images tend to correspond to which prompts and how to steer noise toward those structures. This does not mean the model has an internal gallery of hidden stock photos waiting to be pasted together. Nor does it mean it is reasoning visually as a painter might. It means it has learned a statistical model of images. It can sample from that model under prompt constraints. The outputs can be startlingly original in surface form, while still reflecting the data distribution that shaped the model. The same is true in code generation. A model trained on source code and natural language can learn patterns about syntax, functions, common libraries, algorithm structures, and documentation style. When prompted, it generates code that often looks competent and sometimes is competent. Other times, it produces elegant nonsense with the serene confidence of a junior developer who has not yet met production. Now, before AI starts sounding too competent, let us discuss what it does not do well. Modern models can be astonishing, but their weaknesses are as revealing as their strengths. They may lack robust causal understanding. They may fail on tasks that require precise step-by-step consistency. They may be brittle when prompts are phrased oddly. They may struggle with long reasoning chains unless scaffolded. They may reflect biases present in their training data. They may produce output that sounds impressive while silently drifting away from correctness. These limitations exist partly because the training objective only indirectly encourages many of the things humans care about. A language model learns patterns of reasoning from text, but it is not guaranteed to reason reliably in every case. It learns descriptions of the world, but not grounded physical experience. It learns from averages across huge corpora, not from living through consequences. Humans, for all our mistakes, are embodied creatures with memory, needs, actions, and social accountability. Models are not. They are trained artifacts optimized for performance on certain objectives. This is why current AI is often best understood as narrow, powerful, and uneven. It can outperform humans on some tasks while failing spectacularly on others that seem simple. It can summarize documents in seconds, yet confuse trivial facts. It can generate beautiful images, but mangle hands or symbols. It can write code rapidly, but miss crucial edge cases. Intelligence in machines is not arriving as one smooth, universal thing. It is appearing as a patchwork of capabilities shaped by data, architecture, objectives, interfaces, and deployment constraints. Deployment constraints deserve attention too because real-world AI is not just about training a model in ideal conditions. It is about running that model in production under budgets, latency limits, safety requirements, and unpredictable user behavior. A system deployed in a hospital, bank, factory, school, or vehicle must meet stricter requirements than a demo on a stage. It must be monitored. It must fail gracefully. It must protect privacy. It must handle edge cases. It must often work with incomplete or messy data. The glamorous part of AI is often the demo. The exhausting part is everything after that. This includes data pipelines, labeling processes, evaluation suites, model versioning, bias audits, access controls, caching, inference optimization, observability, retraining cycles, feedback loops, compliance, and human oversight. In other words, the actual functioning of AI in the world depends on far more than a clever model architecture. It depends on engineering systems around the model. That may sound less romantic, but it is also more honest. When a company says it has AI, the reality might range from a fine-tuned large model integrated with retrieval and human review to a glorified rules engine with a few statistical components wearing an AI hat for investors. The label is broad. The implementation is what matters. Another thing that matters is objective mismatch. Sometimes a model appears to do the wrong thing, not because it is broken, but because it is optimizing what it was trained to optimize. And that goal differs from what humans really wanted. This is common in machine learning. If you reward a system for maximizing click-through, it may favor sensational content. If you train a hiring model on past hiring decisions, it may reproduce old biases. If you optimize a recommendation system only for time spent, you may end up with behavior that is excellent for engagement and dreadful for civilization. This is not unique to AI, but AI can amplify it. Models are very good at optimizing patterns once an objective is defined. Humans are often less good at defining objectives that capture our true values. We ask for one thing, then stare in disappointment when the system delivers exactly that in the worst possible way. So AI actually works through optimization, yes, but optimization is only as wise as the objectives, data, and constraints provided. This is one reason safety and alignment research exist. The challenge is not just making systems capable, but making them behave in ways that remain useful, truthful, controllable, fair, and safe under realistic conditions. As we move closer to the next part, we should also talk about memory, because people often assume AI systems remember things the way humans do. Most models do not have persistent memory, unless additional systems are built around them. During a single interaction, the model can use the context window, which contains the current conversation or provided text. But outside that, it does not automatically retain a biography of every exchange. Persistent memory in practical systems often comes from external storage, databases, vector stores, user profiles, logs, and other infrastructure that retrieves relevant past information when needed. So when people imagine a chatbot secretly brooding over yesterday's conversation, the reality is usually more administrative. If the system remembers something, it is because someone engineered a memory mechanism. Otherwise, the model mostly lives in the current context, predicting the next token from the information available at that moment. This turns out to be enough for many tasks, though building longer-term personalization requires more scaffolding, and that is the pattern we keep returning to. The core model is powerful, but incomplete. To create a useful AI system, people wrap it in structures, tools, memory, retrieval, policies, prompts, workflows, interfaces, monitoring. The model is central, but it is rarely the whole story. In the next part, we will go even deeper into what training really looks like at scale, why data curation and evaluation are so difficult, how models can appear to reason, what emergent behavior usually means without making it sound mystical, and why the future of AI may depend as much on system design and governance as on raw model size. For now, the important thing is this: AI actually works by turning inputs into numbers, processing them through learned layers, using attention and other mechanisms to model relationships, and generating outputs based on statistical patterns shaped by large-scale optimization. It can seem eerily human on the surface, but underneath, it is a structured, trainable system for mapping patterns to patterns, a very powerful one, certainly. But still, in the end, a machine of learned probabilities, layered mathematics, and expensive patience. Now, to understand how AI actually works in practice, rather than in glossy diagrams with tasteful gradients, we need to talk about what training really looks like at scale. Because it is one thing to say that a model learns from data, and quite another to picture the industrial process behind that sentence. The phrase makes it sound as if the model sits politely in a chair, reading books, nodding occasionally, and improving itself through contemplation. The truth is more mechanical, more expensive, and much less serene. Training a large model begins long before the first optimization step. First, there is data collection, which is already a world of compromise. What data will be included? In what format? From what sources? How much duplication exists? How much of it is low quality, contradictory, spam-filled, offensive, outdated, machine-generated, legally sensitive, or simply useless? Real-world data is not a dignified library. It is a giant heap of language, images, audio, and code of wildly uneven quality. Somewhere in that heap are extraordinary patterns worth learning. Also, somewhere in that heap are arguments from 2011, broken HTML, dubious recipes, and people being confidently wrong in 3 languages, so the data must be cleaned, filtered, deduplicated, and organized. Documents may be removed if they are too short, too corrupted, too repetitive, or otherwise unhelpful. Offensive or harmful material may be filtered, though never perfectly. Documents may be scored by quality using heuristics or smaller models. Near duplicates may be removed so the model does not overlearn repeated text. Specialized data sets may be blended in for code, mathematics, academic language, or instruction-following behavior. This stage matters enormously because training data is not just quantity, it is diet. Feed the model a better diet, and its later behavior changes in meaningful ways. Then comes the tokenization and batching. The text is broken into tokens, grouped into sequences, and loaded into the training system in enormous batches. During training, the model processes these batches, makes predictions, computes the loss, backpropagates the error, and updates its parameters. This happens again and again and again over vast numbers of steps. The scale is difficult to picture because human intuition is not really designed for billions of examples and trillions of token-level operations. It is designed for remembering where we left our keys and being mildly suspicious of ladders. The actual optimizations process uses backpropagation, which is one of the central algorithms behind neural network training. The name sounds slightly accusatory, but the idea is simple enough. After the model makes a prediction and the loss is computed, the system calculates how much each parameter contributed to the error. It then propagates that information backward through the network, layer by layer, so each weight can be nudged in a direction that should reduce future error. This is how the model learns, not through inspiration, but through millions of microscopic corrections. And these corrections are not clean little revelations. They are noisy, distributed, incremental adjustments in a gigantic system. One update may improve performance on one kind of text while slightly worsening another. A change that helps with syntax may interact oddly with factual recall. A data mixture that improves code performance may shift style elsewhere. Training is not a neat ladder upward. It is more like trying to sculpt a mountain by flicking grains of sand with extraordinary precision while hoping the whole structure does not collapse into nonsense. Large-scale training also introduces the problem of hardware coordination. Models too large for a single device must be spread across many accelerators. Data parallelism, model parallelism, pipeline parallelism, memory sharding, checkpointing, and distributed optimization all become relevant. If one hears these terms and feels immediately sleepy, that is entirely reasonable. But they matter because the impressive behavior of AI is inseparable from the engineering that makes such training possible. The mathematics may define the model, but the infrastructure determines whether that model can actually be trained in finite time without vaporizing the budget. Even once the model is trained, there is the question of when to stop. More training can improve performance, but after a point, it may produce diminishing returns or lead to overfitting on certain data distributions. Researchers monitor metrics on validation sets, examine behavior on benchmarks, and run targeted evaluations. But evaluation is much harder than people sometimes imagine. A benchmark score can be useful, but it is always partial. A model may score well on multiple-choice questions while still failing in open-ended reasoning. It may perform beautifully on known tasks and poorly on real-world user prompts. It may be outstanding in English and mediocre in another language. It may answer mathematics questions well when formatted one way, and become confused when they are phrased naturally. This leads to a subtle but crucial point. AI performance is not one thing. There is no single number that tells you how intelligent a model is in all circumstances. Models have capability profiles. They are better at some types of tasks than others. They may be strong in summarization, decent in coding, weak in long-horizon planning, unreliable in citation generation, excellent at style transfer, and oddly fragile when instructions are layered ambiguously. The public often wants a single answer to the question of whether a model is smart. Engineers usually end up giving the more frustrating but honest answer. Smart at what? Under what conditions? With what tools? On what benchmark? At what latency? And with how much tolerance for error? This is one reason people sometimes speak of emergent behavior. The term is often used to describe capabilities that appear as models get larger and more broadly trained, even if those exact capabilities were not obvious in smaller versions. A model that once barely handled translation may suddenly become competent. A model that could complete sentences may begin solving code tasks. A model that once rambled vaguely may start organizing multi-step explanations. This can feel like the machine has crossed some invisible threshold into new intellectual territory. But we should be careful with the word emergent, because it can make ordinary scaling sound mystical. Many so-called emergent abilities are not supernatural leaps. They are the result of statistical pattern learning, becoming rich enough that new behaviors become visible above the noise. When the model gets bigger, sees more data, and is optimized longer, it acquires internal representations capable of supporting more tasks. That can look sudden when measured against thresholds, but it is still rooted in the same underlying mechanics. No candlelit ceremony occurs. The matrix multiplications merely become more interesting. One of the hardest things to judge in modern AI is reasoning. People often ask whether a model truly reasons or merely imitates reasoning. The answer depends partly on what one means by reasoning, which is a reliably inconvenient complication. If reasoning means producing structured intermediate steps to solve a problem, models can often do that. If reasoning means manipulating abstract relationships and reaching a conclusion not seen verbatim in the training data, models can sometimes do that too. If reasoning means possessing grounded understanding, stable internal world models, and reliable causal planning under changing conditions, the picture becomes much less comfortable. In practice, many language models appear to reason because they have learned patterns of reasoning from text. They have seen explanations, proofs, worked examples, debates, plans, tutorials, derivations, and countless chains of justification. So, when given a problem, they can often generate a plausible sequence of steps. Sometimes, this is genuinely useful and reflects real internal computation over the problem. Other times, it is more like imitating the shape of reasoning without the substance fully holding together. The output sounds careful, but a hidden step may be invalid. The explanation is fluent, but the arithmetic is off. The conclusion has style, but no solid foundation. Researchers have found that prompting models to think step by step can improve performance on some tasks. This is interesting because it suggests that the model benefits from externalized, intermediate reasoning. By generating a chain of thought, the model may better structure the computation required to reach the answer. Yet even this should not be romanticized. The model is not necessarily introspecting in the human sense. It is producing additional text that helps organize the probabilistic process. Useful, yes. Mystical, no. In fact, one of the revealing truths about AI is that a large part of what looks like intelligence may come from representational compression. The model has ingested massive amounts of human-generated structure. It has compressed recurring patterns into distributed parameters. When prompted, it unfolds that compressed structure into new outputs. That can include facts, styles, procedures, patterns of explanation, and fragments of reasoning. A model need not contain a symbolic textbook on logic to produce logical-seeming behavior. It only needs internal machinery capable of mapping certain inputs to certain kinds of structured outputs. Sometimes that is enough. Sometimes it is not. The question of world models also matters here. A world model, loosely speaking, is an internal representation of how things in the world relate and change. Humans have rich world models shaped by bodily interaction, perception, memory, language, and consequence. We know, often implicitly, that objects fall, containers hold things, people have beliefs, doors usually open on hinges, and rain affects sidewalks in ways that tend to be regrettable. AI systems trained only on text acquire indirect world models through descriptions of such regularities. That can go surprisingly far, but it is still secondhand. The model knows the world through language about the world, unless it is trained on other modalities too. This is one reason multimodal AI has become important. Instead of training a model only on text, researchers train systems that process multiple modalities: text, images, audio, video, and sometimes sensor data or actions. A multimodal model can learn correspondences across these forms. It can connect the word cat to visual features of cats, to the sound of people talking about cats, to captions, to scenes, to actions, to questions and answers involving cats, and eventually to richer task behavior. This kind of grounding is still not identical to human experience, but it broadens the model's representational base. Consider how a multimodal assistant might work. An image is fed through a vision encoder that converts it into a learned representation. Text is tokenized and embedded as usual. The system aligns or combines these representations in a shared or coordinated space so that language can refer to visual features and vice versa. The model can then answer questions about the image, generate captions, compare diagrams, interpret screenshots, or follow instructions involving both text and vision. Underneath the elegance of the interface is the same basic story. Convert inputs into numbers, transform them through learned layers, optimize on large datasets, and decode outputs. Video adds yet another level of complexity because time becomes central. Frames are not enough. The system must track changes across sequences, identify actions, maintain context, and distinguish what matters over time. A person standing still is one thing. A person falling is another. A light turning on, a vehicle reversing, a crowd gathering, or an object being left behind all require temporal modeling. Again, models learn statistical patterns, but now across space and time together. This is computationally demanding, which is why video intelligence remains difficult despite the cheerful certainty of many sales decks. The more modalities and tasks a system supports, the more system design begins to matter as much as model design. A general-purpose assistant may need routing logic, tool selection, memory retrieval, safety filters, citation handling, user preference tracking, structured output validation, and fallback mechanisms when uncertainty is high. In other words, the impressive conversation you see may be the visible tip of a much larger pipeline. The model generates language, but other components decide what information it sees, what tools it can use, what formats are allowed, what policies constrain it, and how the answer is checked before it reaches the user. This layered design matters because raw models are often less reliable than polished products. A company may present a fluid AI interface, but the underlying system might include retrieval augmented generation, prompt templates, guardrails, classifiers, re-rankers, external search, structured parsers, and monitoring loops. All of these pieces contribute to what the user experiences as AI. When the system works well, the seams are hidden. When it fails, the seams become educational. Safety and alignment sit right in the middle of this. If AI actually works through optimization, then unsafe behavior can arise whenever the system learns patterns that conflict with human intentions. A model trained on the open internet may absorb harmful instructions, toxic language, manipulative rhetoric, insecure coding practices, and all the other treasures humanity has uploaded. Fine-tuning and safety layers try to reduce such risks. The system may be trained to refuse certain harmful requests, avoid certain categories of content, or steer toward safer phrasing. Additional filters may scan both input and output. Tool permissions may be restricted. Sensitive tasks may require human oversight. Yet none of this is trivial. Alignment is difficult precisely because human preferences are subtle, context-dependent, and internally inconsistent. People want models to be helpful, but not dangerous, honest, but not rude, creative, but not deceptive, safe, but not useless, compliant, but not blindly obedient. These are reasonable desires, but translating them into objective functions and operational rules is not easy. It is the old human problem of wanting nuanced judgment from systems built on finite specifications. AI does not invent this problem. It merely forces us to confront how underspecified many of our values are. There is also the problem of distribution shift. A model may be trained and evaluated on one kind of data, then deployed in an environment where the inputs are different. Maybe the accents are unfamiliar, the image quality is worse, the documents use different formatting, the users ask stranger questions, or the incentives have changed. Performance can degrade sharply outside the training distribution. This is one reason robust deployment requires monitoring. You cannot assume that because the model worked in testing, it will continue working under live conditions. Reality has a habit of introducing edge cases with terrible timing. Monitoring AI systems often involves tracking output quality, latency, usage patterns, failure cases, user feedback, and safety incidents. Logs may be sampled for review. Benchmark suites may be rerun after model updates. Drift detectors may identify changing input distributions. Human evaluators may inspect outputs for subtle errors. In mission-critical settings, confidence thresholds or human approval steps may be required before actions are taken. Again, this sounds less glamorous than visions of digital superintelligence, but it is how dependable systems are actually built. One especially important distinction is between assistive AI and autonomous AI. Many current systems are assistive. They help humans write, summarize, search, analyze, code, classify, or draft. They do not independently decide goals and act across the world for extended periods with open-ended agency. When people worry about AI, they often blur this distinction. A model that drafts emails is one thing. A system that can form plans, access tools, manage money, manipulate users, and pursue objectives persistently is another. Some research is pushing toward more agentic systems, but real autonomy requires additional scaffolding: memory, planning, tool execution, self-monitoring, retry logic, error correction, and goal persistence. Even then, agentic behavior is often more brittle than the demos suggest. A system may plan convincingly in text and then fail at the fourth step because a tool returned an unexpected format or because the environment changed. Human beings also fail at plans, of course, but we tend to notice context more flexibly and improvise using embodied knowledge. AI agents can be impressive in bounded tasks and quietly absurd in open-ended ones. They may optimize the appearance of progress while getting stuck in the loops, which is not entirely unlike some meetings. Another thing people often overlook is latency and cost. An AI model may be highly capable, but if each query is too slow or too expensive, it may not be practical for broad use. Inference optimization therefore becomes a major part of deployment. Techniques such as quantization, distillation, caching, efficient attention mechanisms, speculative decoding, batching, and model serving optimization all help reduce cost and response time. In simple terms, people take a very large model and try to make it faster, cheaper, or smaller without losing too much quality. This can be the difference between a system that is technically impressive and one that is commercially viable. Distillation is a particularly elegant idea. A larger, more capable model can be used to help train a smaller model that mimics some of its behavior. The smaller model may be less capable overall, but much cheaper to run. This reflects a broader truth. The frontier model is not always the one best suited for deployment. Sometimes, a lighter model, paired with good retrieval or domain tuning, is the better engineering choice. The future of AI is not just bigger, it is also more efficient, more specialized, and more integrated. Specialization deserves a moment. General models are impressive because they can do many things. But domain-specific AI often performs better for particular tasks when trained or tuned appropriately. A medical model may learn terminology and document structure better than a generic assistant. A legal model may understand case citations and argument forms more precisely. A retail analytics model may focus on store behavior, detection, counting, and operational events. In industry, value often comes not from the broadest possible intelligence, but from well-designed systems tuned to specific workflows. This is also why claims about AI replacing all human expertise should be treated with caution. Expertise is not just pattern recognition in a vacuum. It includes domain judgment, accountability, tacit knowledge, coordination, ethical responsibility, and understanding of consequences. AI can amplify experts, automate repetitive cognitive tasks, and handle parts of workflows that are structured or pattern-heavy, but replacing the full role is often much harder than replacing a narrow subtask. A radiology assistant that flags suspicious regions on an image is not the same thing as the entire practice of medicine. A coding model that writes boilerplate is not the same thing as software architecture, debugging under pressure, stakeholder communication, and making trade-offs in messy organizations. There is also a deeply human tendency to interpret machine output socially. If a model sounds articulate, we assume it is thoughtful. If it apologizes, we assume it has awareness of error. If it says, "I think," we hear intention. But much of this is interface illusion. The model is trained on human text, so it naturally reproduces human-like conversational forms. It says, "I understand," because that is what such systems are tuned to say in appropriate contexts, not because there is an inner subject having the experience of understanding. This does not make the output useless. It simply means we should not confuse style with ontology. The same caution applies in the opposite direction, though. Some people say that because AI is just statistics, it cannot be doing anything meaningful. But that misses how powerful learned statistical structure can be. Human language, perception, and reasoning themselves contain immense statistical regularities. A system that captures enough of them can produce astonishingly capable behavior. Just statistics is a bit like saying a symphony is just vibrations. True in one sense, but not nearly enough to explain what matters. So where does that leave us? AI actually works through layered statistical learning, optimized over data, shaped by architecture, corrected by losses, improved by scale, tuned by feedback, grounded by tools, constrained by safety systems, and deployed through extensive engineering. It is neither magic nor mere gimmick. It is a family of methods that can compress patterns from the world into models that make useful predictions and generate useful outputs. The difficulty is that useful spans everything from recommending a song to supporting scientific discovery, and the gap between those applications is not small. One of the more interesting frontiers is how AI systems may move from pattern completion toward more robust interaction with the world. That includes longer context, better memory, stronger planning, tool-rich environments, multimodal grounding, and tighter integration with software and physical systems. But each step outward from text generation increases the challenge. Errors become costlier. Verification becomes more important. Safety becomes less optional. A model that invents a fake citation is annoying. A model that mishandles a medical workflow or industrial control system is something else entirely. And that, in a strangely restful way, brings us close to the final part. Because the last piece of how AI actually works is not only how the models are built and trained, but how they fit into human society. Why they are powerful, why they are limited, what they can change, what they cannot, and why the most important questions may not be whether machines can imitate us, but how we choose to use systems that are already very good at imitating some of our most visible skills. In the next part, we will bring the whole thing together. We will talk about what AI is good at, where it still fails, what people usually get wrong about it, what the near future is likely to look like, and why the truth is both less apocalyptic and more transformative than either the enthusiasts or the doom merchants tend to admit. So now we arrive at the last part, where all the machinery, math, data, training, attention, embeddings, evaluation, fine-tuning, and industrial-scale electricity bills have to be brought back to one ordinary question. What does all of this mean in practice? Because once you understand how AI actually works at the technical level, the next thing people usually want to know is whether it is truly intelligent, whether it will replace everyone, whether it understands anything, whether it can be trusted, and whether it is quietly plotting something dramatic in a dimly lit server rack. The calm answer, which is always a bit disappointing to the more theatrical corners of the internet, is that current AI is best understood as a set of powerful pattern learning systems. Some of these systems are now so capable that they can mimic parts of human language, perception, reasoning, and creativity surprisingly well. But the word parts matters. AI does not arrive as a neat copy of a human mind. It arrives as an uneven collection of capabilities, some dazzling, some brittle, some very useful, and some alarmingly eager to invent an answer when silence would have been more dignified. This is why the debate around AI is often so confused. People speak as if there are only two possible positions. Either AI is basically just autocomplete and therefore unimportant, or it is an artificial mind on the verge of replacing civilization with a cleaner and more optimized version of itself. In reality, neither view is satisfying. Just autocomplete understates what large-scale statistical learning can do. Artificial mind overstates what today's systems actually are. Modern AI is powerful enough to matter a great deal without being a human-like consciousness. That is the uncomfortable middle, which is usually where reality prefers to be. Let us begin with what AI is genuinely good at. AI is excellent in domains where there are large amounts of data, clear or learnable patterns and outputs that can be evaluated at least indirectly. Language completion, speech recognition, image classification, anomaly detection, recommendation systems, translation, code assistance, document summarization, visual search, object detection, and many kinds of prediction fall into this broad category. In these settings, AI can often outperform humans on speed, consistency, scale, or even accuracy. It does not get tired. It does not need lunch. It does not become emotionally attached to a bad spreadsheet. These are, from a productivity perspective, regrettably impressive qualities. AI is especially strong when the task has hidden structure that humans find tedious to encode by hand. Consider fraud detection. A bank cannot simply write 1,000 perfectly sufficient rules and be done. Fraud patterns shift. Attackers adapt. Legitimate behavior varies. A model can learn subtle correlations across features and update with new data in ways a fixed rule system cannot easily match. Or consider medical image analysis. A model trained on many scans can pick up patterns too faint or too repetitive for consistent manual screening at scale. Or retail analytics. A computer vision system can count foot traffic, detect queue buildup, identify heat map patterns, and surface store operations data far faster than any human watching live feeds all day would manage without eventually losing faith in fluorescent lighting. AI is also very good at compressing and re-expressing existing information. Summaries, paraphrases, translations, classification labels, semantic search, clustering, transcription, and data extraction all benefit from this. Much of knowledge work involves exactly these activities: reading, sorting, drafting, transforming, retrieving, or explaining information. So, even when AI is not replacing expertise, it can meaningfully change the economics of support work around expertise. A lawyer may still need to think like a lawyer, but the hours spent extracting clauses, comparing drafts, and organizing documents can shrink. A programmer may still need architecture judgment, but boilerplate, test scaffolding, refactoring suggestions, and debugging hints become faster. A teacher may still need pedagogy and human presence, but lesson planning and content adaptation may speed up. The important shift is not always full automation. Often it is capability amplification. That amplification, however, depends on the user understanding where the model is reliable and where it is merely eloquent. This is one of the central tensions in AI adoption. The better a model sounds, the easier it is to trust it too much. Human beings are oddly vulnerable to confidence expressed in full sentences. If a machine speaks clearly, we often relax. If it gives numbered steps, we feel reassured. If it includes a polite transition such as therefore, we begin to suspect rigor. But language models are optimized to produce plausible language. Plausibility and truth overlap often enough to be useful, but not always enough to be safe by default. This means one of the most important practical skills in the AI era may be calibrated trust. Not fear, not worship, not smug dismissal. Calibrated trust. Knowing when the model is likely to help, when it needs verification, when a domain requires external grounding, when a human must stay in the loop, and when a tool-enhanced system is far more trustworthy than a raw generative answer. The future may belong less to people who simply use AI and more to people who know how to supervise it intelligently. This supervision becomes more important in high-stakes domains. If an AI system drafts a social media caption and gets the tone slightly wrong, Civilization survives if an AI system misclassifies a medical case, denies a loan unfairly, misses a safety incident in a factory, or gives dangerously incorrect legal guidance. The consequences are more serious. In such domains, accuracy is not enough on average. Reliability matters case by case. Explainability may matter. Traceability may matter. Auditability matters. The ability to know where the information came from, why a recommendation was made, and how the model behaves under edge conditions becomes central. This is why many serious deployments of AI are not fully autonomous. They are assistive, advisory, or bounded. The model highlights suspicious transactions, but a human investigator decides. The model drafts a report, but a clinician reviews it. The model surfaces risks, but an operator validates the action. In other words, AI often functions best as a force multiplier inside a larger system of human accountability. This is less dramatic than science fiction, but much more likely to survive procurement review. Now, one of the most persistent questions is whether AI understands anything. The answer depends on how strict one is being. If by understanding you mean having a human-like subjective grasp of meaning, intention, and lived context, then no, current AI does not understand in that sense. It has no inner world that we can responsibly describe as experience. It does not sit in reflection after generating a paragraph and quietly wonder whether it was fair to semicolons. But if by understanding you mean having internal representations rich enough to support successful interpretation, inference, and generation across many contexts, then yes, current AI does display a kind of functional understanding. It tracks relationships, context, structure, and abstraction well enough to behave as though it understands many things. This distinction between subjective understanding and functional understanding is easy to miss, but it matters. A calculator does not understand arithmetic in the human sense, yet it performs arithmetic. A chess engine does not appreciate the sorrow of a blunder, yet it understands chess positions in the operational sense that matters for play. Likewise, a language model can understand the structure of a request, the relevance of context, and the relationships among ideas without possessing consciousness. The difficulty is that language is so close to our identity as thinking creatures that when a machine handles language well, we instinctively project personhood into the gap. We hear fluency and assume a self behind it. This may say as much about human psychology as it does about AI. That projection has consequences. Some users become over-attached to conversational systems. Some attribute emotions, intentions, or moral agency where there may only be tuned conversational behavior. Others become suspicious that because the model sounds friendly, it must be manipulative or secretly sentient. In reality, the more grounded view is that these systems are designed to be legible and cooperative in human conversational terms because that is the most practical interface for many tasks. The style is social. The underlying process is computational. Mistaking one for the other leads to confusion in both directions. Another common question is whether AI is creative. Here again, the answer is irritatingly nuanced. AI can certainly generate outputs that humans perceive as creative. Stories, images, music, jokes, designs, code structures, visual compositions, slogans, metaphors, and stylistic combinations that were not explicitly copied from one source. It can recombine learned patterns in novel ways, sometimes with startling effectiveness. Yet its creativity is derivative in a statistical sense. It draws from learned distributions rather than lived intention. It does not create because it is haunted by mortality, or because it once saw winter light on a train platform and needed to express it before the feeling disappeared. It creates because a prompt activated patterns, and the model sampled them coherently. That does not make the output worthless. Much human creativity is also recombination, imitation, synthesis, and transformation. The difference is that human creativity is usually entangled with motives, emotions, constraints, memory, and experience. AI creativity is formal rather than existential. It may produce beautiful things without caring about beauty, which, to be fair, is still more than can be said for some corporate branding committees. Now let us address jobs, because every discussion of AI eventually arrives there, wearing the expression of a worried accountant. Will AI replace workers? In some cases, yes, or at least reduce demand for certain tasks. In other cases, it will change jobs rather than eliminate them. Historically, automation tends to remove or shrink specific tasks first, then reshape roles, then reorganize workflows, and only sometimes eliminate whole occupations. AI appears to be following a similar pattern, though with unusually broad reach into cognitive work. The most immediate effects often fall on routine, repetitive, pattern-heavy, high-volume tasks, basic drafting, entry-level content generation, customer support triage, first-pass data analysis, transcription, document extraction, templated coding, and certain kinds of design iteration. But even there, replacement is not automatic. Quality assurance, domain adaptation, compliance, exception handling, and human oversight remain necessary. Meanwhile, AI creates leverage for more skilled workers who can direct it well. A single competent operator may do the work that once required a larger support team, not because the machine fully replaces judgment, but because it compresses the lower value effort around judgment. This can be economically significant even when it looks modest on paper. If every analyst, lawyer, marketer, developer, designer, teacher, researcher, or operator becomes 20 or 30% more efficient in a meaningful portion of their work, the aggregate effect is enormous. Entire organizations may be redesigned around that productivity shift. Fewer people may be needed for some layers of execution. Higher expectations may be placed on the people who remain. New specialties will emerge: AI orchestration, model operations, data curation, alignment review, prompt engineering. In the broader sense of workflow design, human-AI interaction strategy, synthetic data generation, audit and governance, and domain-specific integration work. The jobs do not simply vanish into mist. They mutate, which is only slightly more comforting. One should also remember that technology adoption is not determined by capability alone. Cost, trust, regulation, workflow friction, organizational inertia, customer preference, and liability all matter. There are many tasks AI can perform in principle that companies will adopt slowly in practice, not because they doubt the model, but because the surrounding system is not ready. A hospital cannot swap in a model the way someone swaps a note-taking app. A bank cannot casually improvise compliance. A government cannot outsource accountability to a chatbot and hope the press fails to notice. Deployment happens where incentives, infrastructure, and risk tolerance permit it. This brings us to governance. If AI actually works by learning from data and optimizing objectives, then society has to decide what data is appropriate, what objectives are acceptable, what uses are allowed, and who bears responsibility when systems fail. These are not technical questions alone. They are legal, ethical, economic, and political. Should AI-generated content be labeled? How should copyrighted training data be handled? What standards should apply to models used in healthcare or law enforcement? Who audits systems for bias or unsafe behavior? How much transparency should companies owe the public about training methods and safety evaluations? These are not side issues. They are part of how AI actually works in the world because the world contains institutions, laws, incentives, and power. The technical truth and the social truth are connected. A model trained on biased historical data may amplify discrimination unless governed carefully. A recommendation engine optimizing engagement may steer public discourse in unhealthy directions unless incentives are checked. A generative model capable of producing persuasive misinformation may complicate trust online unless authentication and provenance systems improve. None of this requires malevolent intent from the model. It follows from optimization plus scale plus weak guardrails. In many ways, the danger of AI is not that it becomes evil. It is that it becomes efficient in the presence of sloppy human goals. That is why alignment is broader than just getting a chatbot to refuse harmful prompts. It is about aligning systems with human purposes, institutional norms, legal obligations, and social values under real conditions. And because those values conflict, alignment is not a puzzle with one elegant solution. It is an ongoing negotiation between capability and control. Another topic people often get wrong is the idea of superintelligence arriving all at once. There is a habit in public discussion of imagining intelligence as a single ladder. The machine climbs upward until it surpasses humans everywhere, and then matters proceed from there in either utopian or catastrophic fashion. But current AI does not look like a single ladder. It looks like a jagged skyline. Some capabilities surge ahead. Others lag badly. A model may write competent code but fail at real-time embodied navigation. It may answer scientific questions but struggle with simple planning in a novel interface. It may crush benchmarks yet get confused by a typo in a spreadsheet header. Intelligence is multidimensional, and machines are advancing unevenly across those dimensions. This does not mean the future will be tame. It means forecasting must be humble. Some capabilities that look hard may fall suddenly with better methods and scaling. Others that seem close may remain stubborn because they require grounding, memory, agency, or robustness we do not yet know how to achieve cheaply. The sensible view is to expect substantial continued progress while resisting both lazy dismissal and prophetic certainty. The people who say AI can never do X and the people who say AI will do literally everything next year are often performing the same mistake with different costumes. What is more certain is that AI will continue moving from standalone models toward integrated systems. The most useful systems will not merely generate text or images. They will connect to software tools, databases, workflows, sensors, enterprise systems, documents, calendars, devices, and user preferences. They will retrieve, reason, plan, act, verify, and escalate. In business environments, the value of AI will often come not from one giant answer model, but from a chain. Detect the event, retrieve the context, classify the issue, call the right service, draft the response, get human approval if needed, log the action, and learn from the outcome. In other words, practical AI will look increasingly like system design with models at key decision points. This is already visible in sectors like customer service, software development, enterprise search, industrial monitoring, retail analytics, finance operations, and digital content production. The model becomes the flexible interpretation layer. It reads messy inputs, maps them to intent, chooses tools, synthesizes outputs, and communicates in natural language. Structured systems do the rest. That combination is powerful precisely because language is such a universal interface. Human instructions are messy, ambiguous, and context-rich. Models are unusually good at handling that mess compared with old, rigid interfaces. This makes AI feel broader than earlier software, even when the downstream actions are still conventional. And yet, the conventional parts remain important. Databases still matter. AP is still matter. Security still matters. Version control, observability, testing, access management, and fallback logic still matter. There is a temptation in some circles to imagine that AI will dissolve the need for software engineering discipline. On the contrary, systems with probabilistic components often require more discipline, not less. When one component may behave differently depending on phrasing or context, the surrounding infrastructure must be designed carefully to constrain failure. Failure, incidentally, deserves a quiet word. AI systems fail in unusual ways. Traditional software often fails discreetly. A null pointer, a timeout, an exception, a broken dependency. AI can fail semantically. It returns something polished but wrong. It misinterprets a prompt with confidence. It gives the right answer for the wrong reason. It produces an image with nearly correct details and one catastrophic absurdity. It classifies almost everything correctly, but systematically fails on a minority case nobody noticed during development. These failures are harder to detect because they do not always crash. They glide. This is why evaluation cannot be an afterthought. Developers need targeted benchmarks, scenario testing, red teaming, human review, uncertainty handling, and domain-specific acceptance criteria. A model that is 95% accurate may still be unacceptable if the remaining 5% includes rare but critical failures. In some contexts, the question is not how often is it right, but when it is wrong, and how detectable is the mistake before harm occurs. That is a much more adult question and therefore less popular in marketing. Let us also talk about memory and personalization one last time, because it shapes how people imagine the future. A truly useful assistant often needs to remember preferences, project context, prior decisions, recurring tasks, and relevant personal or organizational knowledge. But building this well is difficult. Too little memory, and the system feels generic. Too much memory, and it becomes intrusive, brittle, or privacy-threatening. Good memory systems need relevance filtering, permissioning, transparency, update logic, and graceful forgetting. In practice, the future of personalized AI will depend heavily on trustworthy memory design, not just raw model capacity. Privacy in general becomes more important as AI enters workplaces and personal workflows. Models may process sensitive conversations, medical notes, customer data, contracts, camera streams, or internal strategy. That raises questions about storage, retention, access control, on-device versus cloud processing, encryption, audit logs, and regulatory compliance. For many enterprises, the adoption of AI is less constrained by whether the model is impressive and more by whether the data path is acceptable. Sometimes the best model is not the one with the highest benchmark score, but the one that fits the privacy and latency requirements of the deployment environment. That is especially true in edge settings, where AI runs near the device rather than in a central cloud. Cameras, industrial sensors, local gateways, embedded systems, and mobile devices may need real-time inference with limited bandwidth or strict privacy needs. Here, smaller, optimized models become essential. The idea that all AI lives in one enormous data center is incomplete. A great deal of practical AI will be distributed, some perception at the edge, some heavier reasoning in the cloud, some retrieval in enterprise infrastructure, some orchestration across all of it. How AI actually works in these settings becomes not only a modeling question, but a systems architecture question, and that perhaps is the most honest way to close the topic. AI is not one mysterious object. It is a layered stack. At the bottom are mathematics, compute, and data. Above that are model architectures and optimization methods. Above that are fine-tuning, alignment, and evaluation. Above that are tools, memory, retrieval, and orchestration. Above that are products, workflows, businesses, institutions, and laws. And above that, as always, are human beings trying to use a new capability without entirely embarrassing themselves. So when someone asks, how does AI actually work? The shortest respectable answer is this. AI works by learning patterns from data, representing those patterns in mathematical models, and using optimized computations to predict, classify, generate, or decide in ways that can resemble intelligent behavior. The longer and more truthful answer is that these models are trained through large-scale optimization, shaped by data quality and architecture, improved by fine-tuning and human feedback, often grounded with retrieval and tools, constrained by engineering and safety systems, and deployed inside social and organizational structures that determine whether they become useful, harmful, profitable, trusted, or ignored. In practical terms, AI is neither a miracle nor a fraud. It is a real technological shift built on methods that are now strong enough to affect communication, knowledge work, software, vision, science, operations, media, and decision support. It is powerful because pattern learning at scale turns out to be more general than many people expected. It is limited because fluency is not wisdom, prediction is not consciousness, and optimization is not morality. It will likely change a great many things while still leaving a vast amount of human responsibility stubbornly in place. And perhaps that is the most quietly reassuring part. For all the noise around AI, the essential human problems remain recognizably human. What should we optimize? What risks are acceptable? Who gets to decide? What counts as fairness? When should a machine advise rather than act? What must remain under human judgment? Technology can make those questions sharper, but it cannot answer them for us. It can generate options, simulate arguments, compress knowledge, and automate parts of execution. But the larger choices still belong to societies, institutions, and people, which is exhausting naturally, but also appropriate. So the next time you hear AI described as magic, you can picture the much less glamorous truth. Giant data sets, tokenizers, embeddings, attention layers, gradients, weight updates, distributed training runs, evaluation suites, retrieval systems, guardrails, inference servers, and a long chain of engineering decisions trying to turn statistical learning into something useful enough to survive contact with actual life. The machine may sound smooth. Underneath, it is mathematics all the way down. And the next time you hear someone say it is just autocomplete, you can also smile a little and remember that autocomplete, when scaled across much of recorded human language, paired with attention, tools, memory, multimodal learning, and vast optimization, becomes something rather more consequential than the phrase suggests. Not a mind in the human sense, not an oracle, but a new kind of instrument, one that can amplify thought, automate fragments of cognition, and rearrange how people interact with information and work, which, when you really think about it, is already quite a lot for a machine that begins by turning words into numbers. That is how AI actually works. If you want, the next step I can do is turn this full script into a cleaner YouTube narration version with stronger pauses, a calmer intro, and a softer sleep-style ending.